it's just the left side doesn't have to.
You can even give my lecture if you want to.
It's more projectors. It's the whole thing. Certain days.
Oh. It may be
Go away.
the fuse.
What's the call? I had to fix it before.
Mm.
Go away. You have those? Yeah, there's like an input setting where it's like, it's not linked to the actual input. I'm trying to remember. Oh, it's the same as well. Yeah, see, it's not even showing up.
Just to go ahead and go.
Yeah, you can go ahead if you want.
Yeah.
And then you can do it, it's just.
We'll go time. You could say something.
Okay.
我是一个好学生，我有课前预习的习惯。先熟悉一下再讲。
We're out for lunch. Thank you.
Thanks for coming.
Joe, need your help. 126. Yep. It's one of those like this place is not.
It's good timing. One of our bosses was out to lunch, so he's coming over right now. Alright, we'll just wait for this to be in anyway now.
Has this happened here before?
Yeah. Nice.
There he is.
It's off.
You got no power.
Yeah.
We can't fix that. We'll have to call building management.
Is that like
I'll go
lamp?
tell her.
Okay.
Okay.
There's no power there whatsoever.
There's no power coming to that projector at all.
Okay.
I'll go tell the manager.
Yeah, there's nothing we can really do about it in the meantime. That's all right.
So there's nothing I should expect to be fixed in the next 10 minutes because the class is less than an hour, right? So I can.
Yeah.
Yeah. All right.
All right.
But still, the screen, the central screen will come on the video. There is a video now, right?
Yeah.
Yeah. Okay. All right. All right. Thanks, guys.
Yep.
right, too much adrenaline about nothing, you know, too much excitement, videos don't work. And the lecture today is shorter because we already have left maybe 40 minutes. So what I wanted to do is, so I don't get you bored, I wanted to change a little bit subject and get out of Monte Carlo methods, at least for now, and introduce some very fundamental algorithms for statistical computing. And one of those algorithms is what is called expectation maximization. Actually, if you check on the top 10 algorithms of the last century, EM is one of those. And like most important algorithms are usually trivial. Trivial after somebody else does them, right? And then you look back and you say, wow, why it wasn't me? All right, so let's try to motivate the subject. I'm gonna bypass a few things because the lecture is short to be sure that we have something covered today. So let's consider that we go back to the multivariate Gaussian, right? So I just remind you how it looks like. And think of the maximum likelihood estimation we did early on in the course, right? So if somebody gives you a bunch of data, X, that come from this Gaussian, and then tells you, go and compute an estimate of the mean and the variance, these are the MLE estimates. You remember those formulas? All right. Okay, nothing new there. So let me just plot a multivariate Gaussian. And I plot things here in a little bit of a different fashion so we can see what the message of the lecture today is. So I have a mixture of 3 Gaussians, right? This is what we're interested today. So what exactly is plotted on the left? You know, what do you see there on the left? You're going to be fixing something?
We've got maintenance on the way for it. There is an available empty classroom if you want it. Otherwise, there's somebody on their way to turn on that power.
Okay. They don't need to interrupt me. I can keep going, I suppose. And he
Just
can,
wanted to see if you wanted to move over or not.
It's okay.
Okay.
It's all right. It's Friday.
Sorry for the trouble.
Yeah, it's all right. So what do we see on this picture on the left?
Joint probability distribution.
So you see each of these Gaussians separately, right? So you say, if I know this is given the components, all right? This is, you plot the probability for each component, and you see this with red, yellow, and blue. And here, what you see is, you have all the data drawn from this mixture of Gaussians, but you don't really know to what component each of the points belongs. So this is P of X, this is the marginal, right? This is P of X given K. All right? So here you know, so you know which data points come from the red distribution, which ones come from the yellow and the blue. Here is the marginal. I give you a bunch of points. I tell you they come from these 3 components, but I don't tell you which component. Okay? So what you're actually plotting, this marginal looks like this, and you can see the distribution here in 3 dimensions. This is the mixture. So when I give you an X, I don't tell you from where it comes from. It comes from the mixture, but I don't tell you which component it comes from. And so this picture that you see here, these are basically in terms of samples from this Gaussian mixture. So somebody gives you these points, all right? There's no way, we don't have any technique yet, we will do this today, to identify to what Gaussian from the mixture each point belongs. And the way we're going to do this is we're going to do this with by introducing the expectation maximization algorithm. So let me describe this a little bit in detail. This algorithm is universal, all right? It is way as powerful as maximum likelihood estimation, and you can use it for hundreds of different types of problems. So it's not just a Gaussian mixture. So what we have is we have a Gaussian mixture, and the way you actually sample from a Gaussian mixture, right, is you select from which component you want to sample. So you select the index K, and then you take a sample from that Gaussian component, okay? So what you see here is, if you follow this algorithm, you say I'm going to select the red component and then take one sample, or select the yellow, take another sample, or the blue, another sample. So what you see here is samples drawn from the 3 components of the Gaussian mixture. So in reality, this is how you sample from a Gaussian mixture. You first sample from an integer that tells you what component what Gaussian component you're going to work with, and then you take a sample from that Gaussian component, and that's what is plotted here. So here is this, actually it's not even yellow, but I'm colorblind, so it says blue, green, and red. Okay, all right. So we want to do today the inverse problem. So we want, if somebody gives you realization samples from the Gaussian mixture, without telling you from what component of the mixture they're coming, we want to go and compute the mixing coefficients pK, the means of each Gaussian, and the variance of each Gaussian. Okay? So if you remember the equation, it looks like this, the mixture. So somebody gives you realizations of these X points, literally we'll have all of these points, and tells you go and find what pK is, what mu k, and what sigma k for all little k's. That's our problem. Right? So again, the problem is, given samples from the Gaussian mixture, we want to identify the mixing components and the mean and variance of each component. In reality, if you want to make this an interesting problem, and it's not difficult to actually address, I can make that capital K also unknown. Because if you try to represent things with a Gaussian mixture, maybe you don't really know how many mixture components you have. So this is unknown, but right now I'm going to take this as known. All right. I'm going to do this with lots of pictures with colors. All right. So this picture here, it is all the data points are colored, so you know from what mixture component they come. And this is the uncolored data points. And I call this information incomplete because I have not given you the labels of each point. I have not said anything to what component this point belongs. So let me introduce, to be able to address this problem, we have to introduce latent variables. So for every point X, I need to associate a latent variable, and the latent variable will tell me from what mixture component that point X comes from. Make sense? All right? So if, let's say, we have a point xn, it's a sample n, we're going to affiliate these latent variables zkn, right? And zkn, you remember I have a mixture, say, of capital K components. So from all of these components of the vector z, only one is going to be equal to 1, all right? So that way, this point will belong to one of these of the components in the Gaussian mixture. So I denote everything with a vector z, all right, just to make the notation simple, and k takes values from 1 to capital K. So let me explain in a matrix form. Imagine that the column here is each of the data points, and each data point has an affiliated vector z, and the affiliated vector z has only one as a component, the rest is 0. So for example, point 1 is a red point. Point 2 is, a blue point. Point 3 is a green point, etc. So this is the z matrix. But z is a hidden matrix. We don't have that information. We don't really know from what what component of the mixture each data point belongs. So in some ways, we have to compute this. All right, so it's extremely valuable, very important problem. Okay, so before, we know this conditional distribution. If I give you z, you know the distribution of x is Gaussian, right? It's one of the Gaussian components. So what I would like to do is, I would like to also introduce the concept of the joint distribution of x and z, and simply write it with the product rule as p of x given c times p of z. All right. This is the Gaussian mixture. Okay. So we introduce for every data point x, we introduce a latent variable z. This is the joint distribution. We already call this the mixing coefficients. And let me introduce this as a prior, if you like. The probability of z is the product over the little k from k1 to capital K of the mixing coefficients, the power zk. So I want you to look at this equation and tell me that you understand what it says. Remember, the zk is a vector, right? And it has everything 0 except one component that is 1. So would you look at this, like, for example, for this z vector, only this component is equal to 1. So if you write the product over all the components, red, green, blue, and you multiply them, which component are you going to extract from this formula? All the z's are going to be 0 except the red, so you're going to get p red. And this is actually, isn't it the prior probability that you're going to be red? Because we have in the Gaussian mixture, this is the probability a priori that defines the weights, if you like, of the red component, the green component, and the blue component. So the way you write the prior in a compact way is P of z is the product of all possible states. In this case, we have 3 of pk to the power zk. All right? The idea here is, right, if you write it this way, it's a universal formula. I don't have to write anything specific. So, product over all the states, that's the same for everything. And then these are the mixing coefficients to power zk. So from this zk, when I take this product, only one component is going to be 1, and then I'm going to pick up the mixing coefficient, which is the prior for z. Okay? Yes? No? Yes? All right, it's Friday. Okay, so you're tired. All right. Okay, and the conditional distribution, basically, if I knew that zk is equal to 1, right, that the k component of z is equal to 1, then obviously this conditional distribution is the Gaussian that corresponds, is the kth component in the Gaussian mixture. All right, so similarly, if I knew z, I am going to write the conditional distribution of the observations given z with this nice formula. So look at this and tell me, if you knew z, does this formula make sense? You remember, if you knew z means if you knew that your x point comes from the green Gaussian, the red Gaussian, the blue Gaussian, is this correct? Because from the z case, you will get only 1, right? So let's say if z green is equal to 1, you're going to get the green Gaussian. Okay? All right, so we have p of xz like that, p of z like that. So the joint distribution, if you multiply them, you get the product of all the states, of all the colors, of pk times n of xk and k sigma k to the power sigma k. And just to show you that the calculation we have done here is correct, right? If you go and you marginalize over z, right, you actually are going to get the Gaussian mixture. And the calculation is sort of worth doing it, or you don't have to do anything actually, you can just look at it. If you integrate in z, you actually get the Gaussian mixture the way you're supposed to, okay? So this is the joint, if you knew the z variables, and this is, the marginal where z has been integrated out. So how from there you actually get this? This is very simple to see, because what you need to do is you need to integrate over all possible values of z. Right? This is how you marginalize. And let's say for our specific example of the 3 colors, what are the 3 possible values of z? 1, 0, 0, 0, 1, 0, 0, 0, 1. Correct? So take this formula and sum for all possible values of z, where the first value is 1, 0, 0. What will that give you? Which component will that give you? Huh? the first one, we give P1 times n of x given mu1 sigma 1, and then if you take 0, 1, 0, you get the second, then the third, and there is the Gaussian mixture. So you may say, what have I gained by introducing these latent variables? Then you tell us about if I integrate z, I get this. Well, you will see in a second why working with this is computationally very difficult. Working with that is computationally very easy. And that's why we need a new algorithm to work on these problems. All right, so let me, a little bit ahead of in the slides here, let me introduce the concept of the responsibilities. All right, that's the name of the variable. So for a given point x, the responsibility is nothing else but the posterior probability of z for that point x. Okay, so if I have a given point x with given parameters in the mixture, so the mean, the variances, etc., if they are fixed, it is the posterior probability of z given x. And the way that it is written here, right, is I used basically Bayes' rule. So this is the prior, this is the likelihood, and this is the normalization factor. So look at this and tell me what exactly, give me an interpretation. What does this tell you? So think, so the vector z, right, in our case, has three components. So let's say, what is the posterior probability that z red equal to 1? How do you interpret that? So what's the meaning? What's the posterior probability? What is this probability means that the posterior of z, and actually, you know what? I will come back to this, okay? I should remove that one there, right? I should remove that one there. Should not say equal to 1. So what is the posterior of zk given, well, actually, it is fine because I'm referring here, okay, so what's the posterior that z red equal to 1 for a given x? How do you interpret it? I mean, before we had this prior probability, pi red, right, in the mixture component, let's say pi 1, and now I have the posterior. So the idea here is once you have seen x, all right, what responsibility the red component of the mixture takes in interpreting the value of x. That's why we call it responsibility. Okay, so it is the posterior probability basically that the point x belongs to the red component, okay, and it's given basically by the mixing red coefficient times this red Gaussian divided by this normalization factor. So let me explain this, with graphics here. So this is the marginal distribution of p of x that we had before, where all points have the same color. We don't know which point belongs to what. This is the joint distribution. So for each point, we know the color. We know z. So we know these points are the red points, these are the greens, these are the blue, right? So this is the joint distribution. And at this graph here, all right, how many colors do you think I have in this plot? Look at I'm colorblind, right? But do we actually have red, blue, and green? Only? There's more?
Well, there's like mixture.
This mixture. So what does that mixture mean? Because you remember, for each point, each component takes a responsibility in explaining it. One component will tell you I take 50% responsibility, another one 30, and another one 20. So when you plot this thing here, the colors that you use for each point are proportional to the responsibilities that each Gaussian takes in explaining the given point x. Make sense? All right. So actually, it would be nice if you do a plot like that. I give you the homework, but you really have to be able to plot things with colors that are a mixture of colors, and you can easily do this with MATLAB and other software. Okay, so let me continue to see why playing with the Gaussian mixture is complicated. So if you remember, when you have unknown parameters, and in our case, the mixing coefficients are not known, the means and the variances in each component are not known, so we need to compute them. So if you try to do MLE, maximum likelihood, what you will do is you will take, let's say, the log likelihood and try to maximize it with respect to each of the parameters. So if we take the log likelihood, so X, capital X are all the data, and we write this as a function of the parameters, we're going to have its log likelihood, so the products become summations. We're going to have summation of the log, and you remember the likelihood here, it's a mixture. You see this? And there is the difficulty, because you have a summation over these components inside the log. So you have the standard complicated problem in machine learning where you have log sum, right? You have the log of a sum. That's very difficult to work with. And it's a universal problem that comes in not here only, but in many other areas where you have hidden variables actually facilitate to address this. But here we have a summation, and then we have an operation with a log of the summation, so that is very difficult. So actually, if you try to do MLE with this, you realize you're not going to go anywhere. It's not going to work. Okay? So, and let me tell you another problem that it's standard basically for this type of MLE things. So in MLE, right, we try to maximize the likelihood. Okay? So let me give you a very easy scenario to define these Gaussians in a way that I will make the likelihood infinite, right? Maximize, I will make it infinite. So here are the data points that I have. You know what I'm going to do is, I'm going to put a likelihood, I'm going to put a Gaussian, one of the Gaussian components to be centered exactly in one of these data points, and I'm going to make the variance to go to 0. So like a delta function around each point. And if you do that, notice the exponential will give you 1, and because sigma goes to 0, then each component goes to infinity. I maximize the likelihood. You see this? You see why basically if you try to maximize the likelihood, it's not going to help you, because you may get pathologies that look like this. So as you try to iteratively do things, you may get a situation where somehow the likelihood goes to infinity. Not only that, if the number of components is not fixed, right, and we say, why should I have 3? I can have 23. The more components you have, the higher the likelihood will be. So actually, you will never be able to find the right solution. So how do I address this problem? There are other, of course, there are other complications that I will not elaborate today. And one of these complications is that you cannot uniquely identify the number of components. For example, I'm colorblind, right? I told you this is the red component, this is the green, and this is the blue. And you come and you say to me, you must be kidding. This is the yellow, this is the green, and this is the blue. Right? It's a different solution. So how will the code know and say, this is the mean of this, the mean of that? Well, you're going to have k factorial equivalent solutions. So you will find one of those. Okay? So that's another problem, the identifiability, to be able to identify basically which component is what is an issue. Okay. So let me start doing some calculations first. So this is the way we introduce the log likelihood. So this symbol here is the likelihood. The log likelihood is a summation of the log of the sum of the Gaussian mixture. Okay. And to make the notation simple, for each data point n, this Gaussian I denote it here as n and k. So k basically gives you the component in the mixture, and n refers to the point, the out of capital N points in the likelihood. Okay, so I call this n and k. So if you take the derivative of this, let's say you want to find the mean of one of the components. So you're going to take derivatives with respect to mean and set it equal to 0. So how do you, so you're going to have a summation outside. Log, how do you take derivatives of the log? Is 1 over this times this pi times the derivative of this Gaussian with respect to the mean. So you agree, right, from the mixture components, only the j component is going to have relevance to mu j, the rest will not give you any contributions. And what I have done here is I multiply and divide by this n and j, all right? And I'm going to give a nice name to this, and I can tell you now that this is going to come up actually to be our posterior probabilities, what I call responsibilities. So this will be the responsibility the j component is taking in explaining point n, okay? But for now, just call this thing gamma of z and j, okay? And if you do this from the Gaussian exactly, the calculation, you get sigma j inverse xn minus mj, and then you get mj equal to this result. So actually this is what you will get with MLE, and I want you to look on the formula and tell me how this relates to the MLE estimate. So that way we can get an interpretation of what is going on. So look at this equation and tell me how does it differ from MLE. In MLE, when you have Gaussian, you have data points, how do you compute the mean? What's the mean of, for a Gaussian? It's the empirical mean, it's the sum of all the points divided by all the points. Here, you notice each point is weighted with the responsibility of the j component in the mixture. So basically, to find the mean of the j Gaussian is like doing MLE, but actually instead of using here 1 and here all the number of points, you weight each point with how much it belongs to the mixture j. You see that? I mean, this point n, right? It may belong just to the red component, okay, and nowhere else. And so in that case, what you will get is summation of the red points divided by the number of the red points. But, you know, some of the points may be partially red, partially blue. So you weight basically all the points. This is all the points with how much they belong to the component j, and that's how you get mj. Okay? So very simple interpretation of what you get. Now, there is a complication of this formula that doesn't make it directly very useful, and the complication is these responsibilities, as I call them here. If you look at the definition that I use, gamma depends actually on, I mean, looking only on the denominator, it depends on all the parameters. It depends on the mixing coefficients pi, on the means and the variances. So this formula is like telling you the mean is a function of the mean of j and all the other means and all the other variances which you don't know. So you have to do this iteratively, self-consistently. So in other ways, fix the means and the variances and the mixing coefficients, compute gamma, then update and get mu, then update again gamma, then do mu, and this will give us an idea of how the expectation maximization algorithm works. So here is the idea of the expectation maximization algorithm. I am not going to give you why we call the two steps expectation, why this is called EM yet, okay, you will see this. So in the E step, we basically fix all the parameters and we compute the responsibilities for each data point. And on the M step, we basically update the parameters for given responsibilities, okay? And we keep iterating until this thing converges. All right. Let me just, so if you, you know, to give you an idea of, since we computed the mean, if you take derivatives with respect to the mixing coefficients or with respect to the variances, these are the formulas that you get. So everything is expected, because if you look at the variance, for a single Gaussian, everything would be the empirical variance. For this would be equal to 1, and here you be n. Here what you do is you take all the points let's say if you look for the variance, the covariance in the red mix component, you still take all the points, but you weight each point with how much it belongs to the red color, okay? And the way you do this is using the responsibilities, which are posterior probabilities that point N belongs to the component J, okay? You know, this is again the same derivation. The derivation for the mixing coefficients is slightly a little bit more elaborate. You still maximize the likelihood, but you, as always you do with mixing coefficients, you have to enforce that all the pi k sum to 1, okay? So if you do this and you augment your likelihood with this term using Lagrange multiplier lambda in 2-3 steps, you know, you get basically this nice formula that says the mixing component, the pi k, let's say pi red is this term divided by capital N. So how do you understand this for k being red? You look at all the points and you sum the responsibility the red color is taking to explain all the points. So it's like the equivalent number of points that belong to the red color divided by N. Okay? But again, some points will contribute to the red, to the blue, to the green, all right? And everything is accounted in this nice formula. So Nk is the number of points that are affiliated with the K component, and it is summation of these responsibilities that you see there. This is a standard example that is listed in practically all machine learning books. It's the All Faithful data set. The horizontal axis is the duration of eruptions. On the vertical axis is the time between eruptions, and this is the unlabeled data points that you have. And basically what you want to do is you want to fit a mixture of two Gaussians on this, okay? And you want to do this using the EM algorithm. So let's see how the EM algorithm actually works. In the E step, what we will do is, right, we will compute, okay? First, we fix the parameters of the two Gaussians. So what I do is, I say one Gaussian is this, and another Gaussian is that. You don't do it really arbitrarily, but let's say you fix them. You know, you say this is one Gaussian, this is another Gaussian. In the second step, what you will do is, you will compute for these two Gaussians, you will compute the responsibilities. So each point, how much it belongs to the blue Gaussian and how much it belongs to the red Gaussian. And you can see these are obviously the way it comes. They're closer to the red, they are red. These are blue, and somewhere in between, it's a mixture of the two. Okay? What is the next step going to be now? So we colored now the points. So we're going to fix the responsibility. So what should we do next? We're going to update now the two Gaussians. We're going to update the mean and the variances. How do we update them? Using these formulas that I gave you before, all of these formulas. Okay? So if we update, let's see what happens. Suddenly the two Gaussians become these two blues and reds. Now we fix those two, and what do? We change the colors. All right, we are going to update this, and you notice going from there to there, the two Gaussians remain constant, right? We don't change mean or variance or anything like that. The coloring of the point changes, okay? The coloring of the point changes. And we continue doing this, and after 20 iterations, basically you get one Gaussian there, one Gaussian there, and actually very few points from what I see here belong to the two Gaussians because the points are a little bit separated. Okay, so this is another implementation if you want to see this in action. Certainly you can see some points here, they are not red, they are not blue, it's a mixture of the two colors, and this is for different steps of the algorithm, okay? All right, and so when you finish, all right, I mean, I did this for two Gaussian components, right? But you can see when you do this eventually for three, you start from points that they were unlabeled, and now you have the points with the markers that tell you from what Gaussian component they came from. So very nice, extremely useful algorithm. Okay, there is no really proof on that the expectation maximization will actually give you the global, if you like, maximum of the likelihood. So no guarantees on that. I don't know theoretically if there are actually guarantees that it will converge, but in most of the problems with Gaussian mixtures and all of these things, it actually works nicely. And there is a lot of guidance on the slides that I will post this afternoon that tells you actually how to start the algorithm to make it to converge very fast. Okay, so and I give you another program that does the same example actually from, And if you want to look at the likelihood, basically you can see actually in this particular case, the maximum likelihood basically is satisfied because you basically have reached an asymptotic. So you don't have sort of oscillations between iterations. It converges quite fast in 8 iterations. Okay. So let me, we have a few minutes left, or until the light goes off. So let's try to generalize this and see exactly what have we done, and put some more fundamental, more fundamental algorithms behind expectation maximization. So what you see again here is the log likelihood, and we said this is not very tractable because we have log of a summation. So this, in general, is very complicated to work with. So we're going to work instead with the joint likelihood. We will pretend that we know the colors of each point, and we're going to work with this, the log likelihood, if you like, of the two variables x and z. This is the joint log likelihood. Now you may say, well, you cannot do MLE on this because you don't know the z, right? So you cannot do MLE because you don't know the z. And I'm going to say that's true. You don't know the z. What is the only thing you mean we demonstrated that we can compute iteratively about z? So in all the discussion, what do we know, or what can we compute about z? What were the responsibilities? We can compute for each point x, right? We can compute the posterior of z, right? So we said this is not computationally very tractable. This is very nice because this is extremely easy distribution to work if you knew z, but you don't know z. So it would be nice if we can maximize this, but we cannot, right? We cannot maximize this. But you know what? Can we maximize the expectation of the joint log likelihood with respect to the posterior of z? Let me repeat. We cannot really do likelihood on this, right? Because we don't know z. How can we get rid of z? We can get rid of z, instead of working with the log likelihood, the joint log likelihood, we work with the expected value of the joint log likelihood, expected value with respect to the posterior of z. Make sense? So how that works? Here is the key idea. So this is the log likelihood, all right? And in this case, because we work with the red, the blue, the green colors, z is a discrete variable. So this is the responsibilities. And you notice I compute the responsibilities with respect to the previous estimate of the parameters, right? Because we anticipate that we're going to be doing this as before iteratively. So the log likelihood, the joint log likelihood, is defined for the unknown means and mixing coefficients, but the posterior is defined using the previous parameters. So what is this Q? Is the expected complete data log likelihood. Okay? The word complete data means x and z. All right? Because here, when I write this, right, means I know x, I know z. Okay? So this is the complete data log likelihood. The parameters there are unknown, okay? But when I average to get an expectation, I take the posterior of z, and I have computed the posterior of z using the previous values of the parameters, some old parameters. Because the idea here is, I am going to iterate, right? I'm going to update the parameters, then compute this again, then maximize this, then update the parameters, get this again, do this calculation, maximize, etc. So, here's the algorithm. Step 1, compute in the step the responsibilities with all the parameters fixed. So you fix the parameters, you fix the means of the Gaussian, the covariances, the mixing coefficients, and you compute the posterior of z, okay? And then you compute the expected joint log likelihood, right? You compute this quantity q here. What is the m step? You take the derivatives of, you maximize basically q with respect to the parameters theta. You update basically then back theta all to be the theta nu. You come back to the step. You compute the responsibilities again. You compute the expected joint log likelihood. You maximize it. You update. You come back. That's the EM algorithm. This idea, it sounds sort of a little bit trivial and naive, but it's basically behind hundreds, thousands of different sorts of implementation in statistics on extremely important problems that you will see if you take other courses. So this algorithm is as trivial as it looks. It has lots of deep concepts, right? One of the deep concepts is the joint log likelihood, the fact that you take the expectation with respect to the posterior, and because I know the light is going to disappear. Well, I mean, if you do this algorithm, basically you will get the values that I had before. You can actually make this algorithm fully Bayesian. So when you maximize that quantity q with respect to the parameters, you can put some prior on the parameters. So this will be like a map estimate, if you like. All right. So you can do that as well. And now I mentioned that the joint log likelihood is very simple to work with, and here is why. This is the joint log likelihood, all right? And if you take logs, the product becomes summation, the z is going to become on the front, okay? So what you actually have is, z and k of the log of pk times what we called before n and k. There's no summation here anymore, right? The summation over the mixture has disappeared, right? So basically what you have is summation on n, summation of k of z and k times this nice two terms. All right, so what I'm going to do is I'm going to abandon you there, and I am not going to be here on Tuesday, but I will ask Suvik to continue this lecture on the EM algorithm, and then give you some examples on applying it to different problems with images, and also some extensions that they're very relevant to variational methods. So I'm going to post the slides, look at them, and we will continue on this on Tuesday.
Oh, yeah. There are pulled out. My mom bought these for me and my sister during the craze when they were really popular. And so they didn't have any women's size. Just a reminder of parents. And they're kind of wide. Yeah, they're really nice.
Thank you.